Okay, yeah. So last time we finished up the exceptions, and now we're moving on to memory and the call stack. Before getting into this, what I'm about to explain, these are important concepts, but if you needed to prioritize what do I need to commit to memory, this is not as important as the other things. This is to just give you a sense of how things are working under the hood, but they don't. This isn't like this isn't on the exam type thing. It's just to give you a sense of how things are working in the back end. When we get to the call stack, though, that of course will be important. Keep my Will Smith did join. Oh, yeah. Hey. All right. Memory in the call stack. Okay, when running programs on our computer, memory is used and accessed in different ways. And by the way, there's going to be a lot of jargon used, and there's probably been a lot of jargon I've used that I may have taken for granted that you know that you might very well not know. So if that's the case, if I'm using words that you're just like, wait, okay, like what's the difference between memory and RAM, you know? If you have any of those questions during this lecture, you throw them in the chat and we'll see if we can kind of fill in those gaps. Okay. Someone tweeted, the only reason Will did it was because Uncle crap, what's his name? Uncle Phil, thank you. Uncle Phil isn't around to whoop him anymore. All right. And also, I appreciate that conspiracy theory. That's big brain right there. Because they were complaining about ratings to begin with, so. All right, back to content. When running programs on your computer, memory is used and accessed in different ways. So typically, we are physically storing instructions and data in the same address space. Now, there are multiple different architectures and strategies one could use for physically designing their computing system. The one we use has this shared instruction and data memory, which some people would be like, well, that's a recipe for disaster, which it totally could be, but for many programming languages, Java included, we logically separate which parts of that memory are for your data and for instructions. And when I say data and instructions, I mean every line of code you write needs to get stored in memory so your computer knows what it's doing. And then the data that your program is using is also stored in memory as well. Yeah. And when I say like physically stored, you gotta know, like we have transistors that are kind of like a bunch of little switches that are configured in certain ways that can represent everything in our computer. So we physically have these like low voltages and high voltages. So keep in mind, like this isn't just like, oh, virtual. Like, well, yeah, but at the end of the day, it's physically represented in our computers. Okay, this could be a recipe for disaster, blah, blah, blah. Okay. Dynamic. Okay. For many programming languages, Java included, we logically separate memory into areas for instructions, dynamically allocated stuff, and stuff related to what's currently happening. Okay. So you can kind of think of it as like, okay, well, I've got all this storage. Some of it's over here for like the instructions. Some of it's over here for like all of the data and whatnot I need to keep track of. And some of it's stored like right in front of me on my little desk for the stuff that I'm currently working on. All right, so this content is kept very high level for introductory purposes. There may be some asterisks added to many of the statements contained within. Point being, we can keep this a very abstract high-level discussion, or we can play the game of like, but, and work our way down to the insane nitty-gritty it's been a long time since I even cared about that stuff. So I'll just warn you that this is not, this is not going to be like low level nitty gritty. You'll learn that stuff like next year. All right, so memory allocation. Memory is broken down into two very broad sections, the stack and the heap, okay? The stack is literally a stack, like the data structure we've been playing with. It's a stack. You ever run your program and you see, well, I'll get to that later. So the stack is what's storing information about the current methods that are being run. It's going to store local variables, the parameters for your methods, and like the return addresses. Because like every time a function is called, the function needs to know where to return the value to, right? If it's returning something. And then there's the heap, which can be broken down further into storage for static information and instance information. Static information, that's like your code. The code that's just like there. That's not changing, it's there. And then instance information. Things like where objects are stored. And technically in Java, you can break this down further into longer living objects and an area for younger objects, but we're gonna ignore that because that has to deal with garbage collection and a lot of technicalities. So this is a visualization of how we are logically separating our memory. We have the call stack. This is what your program's doing. Like this is like what it's currently like working on. And in the call stack, every time you make a new method call, you push like they call it like a call frame or a data frame. And I think there's a third word that they'll sometimes use. Every time you make a method call, you push it on the stack. And so if you have a method that calls another method, that calls another method, that calls another method, I mean, that's a lot of methods calling methods. Well, they just get pushed onto the stack. And as soon as the method's being done, it gets popped off the stack. So that's kind of cool. I'm going to skip this one here just for a quick moment and then talk about the static space. This is the part of the heap that is storing like your code in the instructions. And then we've got the objects in the heap. So this is, you know how everything in Java is an object? Everything is a reference variable unless it's a primitive type. Yeah, that's because those things are stored in the heap. They are dynamically allocated because your computer needs to decide how much RAM it needs to store specific things. So it just sets aside the RAM. It's like, okay, I'm going to store it over here in memory, and then I'm going to give you a reference to it. Because, I don't know, giant objects, you can't really fit nicely in your stack. That is not a very technical explanation, but okay. So for example, if we were to run sorted bag, my bag equals a new array sorted stack, in my main method, the information on what an array sorted bag is oh no, I guess that's correct, is stored in the static area of the heap. So the code that defines what an array sorted bag is stored in this blue bit. The array sorted bag that is created is put into the instance area of the heap right here. So the actual bag object is stored in the heap. But you're going to, like, if you're in your main method, you're going to be making use of your bag for whatever reason. So the reference variable to the array sorted bag is stored in the stack. I think I heard a couple of boops. The people who designed all this stuff were goddamn geniuses. They were, they needed to go outside more, I think, but whatever, we benefited from it. Remember though, Bilbo, that Java, I meant, don't we all at the end of the day? Yeah. You got to remember that Java is it's not new. It's been around since like the 89, 90 or something. When did Java come out? 91. Okay, Java was first released in 95, which is interesting because Python's older. People don't realize that. '91. A lot of people assume Java's older than Python, but it's not. Java and Python. I mean, you might say like, wow, the 90s, that is a little while ago, right? That's not new. Yeah, but Python has a new version every month. Same with Java. We're about to get like Java, when is it? Java 18? When does Java 18 come out? Or are we currently on? 6 days ago? Oracle announces Java 18. There we go. Look at that. Java 18 is here. Look at that. Literally days ago. Huh. So I got you there, Noah. But anyways, point being, these are relatively new languages. And when I say relatively new, it's because we're not going back to the time of like Fortran or C or any of these older ones that required a lot more like wrestling than these newer ones. Because, I mean, I'm kind of with you because that's, Java and Python are languages designed for two very different things, though. And we can get into discussion of that, but let's save that for a little later. You don't use Python to run big applications and software. That's just you're wasting a lot of resources. In fact, Python is actually one of the worst programming languages for the environment due to its electricity consumption in order to do everything it does. So, FYI, we switched to Java to save the planet. But these are relatively new languages that also get new versions every now and then. So they had the luxury of looking at what the previous languages did well and didn't do well. And then since then, they've been able to look at what they did well. And X is a green school. There you go. One programming language at a time. So yeah, these languages, like if you think someone sat down and engineered this idea from day one, they didn't. There was a lot of learning and figuring out what worked. Now, what's kind of neat though, is Java and Python will work very similar in terms of how their memory is divvied up. But in other languages like C++, for example, you can put objects in the heap or the stack. You could put primitive types in the heap or the stack. It all depends on where you, the programmer, says you want to put things. Now, a lot of these more modern languages kind of were like, well, that's dumb. Why would you, like, just don't do that. We'll restrict it to this. And that's why things are kind of nicer and cleaner. By the way, I'm kind of curious, has anyone gone and looked through any of the C++ lessons? There is a fifth one that is half out. Can't remember what it's called. Has anyone gone and looked through these? They're not important that you do right now or anything. I'm just kind of curious because I'm putting them there. The reason I'm putting them there is because, one, if you are, where did you all go? There we go. Raise your hand if you are, listen to everything. Raise your hand. Oh. If you are 1, in engineering, 2, going to Dow next year, and 3, will be taking more programming courses. Raise your hand. Holy moly. Okay, so y'all better get used to C++ because that's what they're going to make you use. So as a primer for you, I have added these C++ lessons, and there'll be a couple more lessons I'll add. What's cool about this though is with C++, like, it's remarkably similar to Python and Java, but I just kind of point out some of the extra little nuances there for you. Now, raise your hand if you are not going to Dow next year, or raise your hand if you're going to take Computer Science 255 next year, which is the class that comes after this. Okay, so for those of you that just raised your hand, there's a damn good chance that you will be learning in C++, which again, I made the references there for you. If the hardest part of 162 is the core underlying concepts. And the core underlying concepts are the same if you're using Python, Java, C++, C#, whatever. They are the same. So that's what's important here. Other than that, the language differences are just little nuances that you pick up pretty quickly. If you know what you want to do, you just don't know how to do it in C++. Like if you're like, I want to build a stack. I know what a stack is. I know how to do it, but I want to build one in C++. Just you start throwing things into Google, next you know you've got a stack. It's fine. Yeah. Now, for those of you that are doing engineering and will be going to, okay, let's put your hands back down and raise your hands again if you're going to be doing engineering and going to Dal next year and taking more programming courses. And leave your hand up for a sec. See, and that's just it. Guess number 4 is right. The first couple languages you learn, it definitely feels like, what the hell? And then you quickly kind of pick up, oh, it's basically exactly the same. Just, I got to do that there and this there and this there. So I feel like Ruby is, yes, but that's just it. C# is as well. Remember when I showed you that thing about like many of these like your object-oriented and procedural languages are very, 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 very similar. It's not until you get to weird languages like Haskell, which are functional languages, where you see some big differences. Okay, hold on. Last time people put their hand up, there were way more people raising their hand going in engineering for Dal. Raise your hands. Looks like we've lost hands. I swear to God, there were a lot more the first time I did it, but whatever. For those of you that are going to Dal next year, what can I do to convince you not to and to stay here and do computer science? Because it's way better. But jokes aside, do computer science, it's better. But let's get back to the topic. F+++, what? That's what I'm doing, haha. Computer science? Yeah, you are. It is better. All right, what is this? Warning, your power connector is not plugged in properly. Oh, let's try that again. Sorry. All right, that was weird. Probably. Okay, back to content. Okay, the call stack. So the call stack is going to be the biggest takeaway from today, I'd say. The call stack is the part of memory where the information about the current methods being run is stored, along with the other methods that are running, but are waiting on the current method to finish, right? Because if you have a method calling another method, the called method has to complete and return to the calling method before it can resume. So the thing at the top of the stack is what's currently being run, and everything below is waiting for the thing above it to finish before it can carry on. So at the end, like in any program, here's a quick little quiz for all of you worth no points. What is at the bottom of every single call stack for any Java program you write? What is at the bottom? Not the top, the bottom. Uh-oh, I've stumped you. What is the first method that gets run in every program? Constructor, no. But I mean, your head's in the right place. Main, that's right, main. It's the main. Constructor was a reasonable guess, but main. Because main is where your program starts. And then your main's gonna call methods, which might call other methods, which might call other methods. And that's how your call stack grows and shrinks. All right. Okay. Along with the other methods that we're running, but okay. The call stack is also a stack. We push and pop information. You all have been using your mental stack throughout your life. I got a YouTube link here. Oh God, yeah, that's a good joke. All right, I'll leave that there though. Ever been debugging to deal with a bug, with bug A, then notice that to solve it, you need to fix B, and then to fix B, you need to resolve C. Then once C is fixed, you can fix B, then B is fixed and you can fix A. I mean, you use your mental stack all of the time. all of the time. Whether you like it or not, you are. And this is a pretty good joke. I like this one. Where he goes to fix something and every 2 seconds he discovers a new problem that he has to fix. And so he just keeps pushing things. Oh no. Did I close? I closed the course content. Well, whatever. He just keeps pushing things to fix on his call stack. All right, let's go back to memory and the call stack. Okay, call frame. So each time we start running a new method, a call frame containing the relevant information for that method is created and pushed onto the stack. And the call frame contains important information for the execution of that method. It's got space for the parameters that are passed to the method, like variables, right? Space for local variables, right? If the data type is a primitive type, then the data is literally stored there. But if it's an object, then we know it's a reference variable to something in the heap. But the reference variable is stored in the call frame on the call stack. And memory address of where the program returns to when the method finishes, where the calling method's call frame can be found in memory. Right. So when the running method finishes, it's popped from the stack and the memory it used is deallocated. And it's automatically deallocated for us. So that's nice. I mean, in Java, things are deallocated for us in the heap, but you know, the garbage collection has to do it. But if we go and look at this little example here, I've got my main that calls function 1, and then function 1 calls function 2 and function 3. But let's go check out function 2 first. Function 2 calls function 4. Then function 2 finishes. Function 3 doesn't do anything. Okay, so if we watch this, this little GIF is kind of showing what is on and off the call stack. And of course, when the program finishes, the main is popped off the stack. So what we should see is main, function 1, function 2, and then function 2 calls function 4. Function 4 finishes, returns to function 2. Function 2 finishes, returns to function 1, which then pushes on function 3. We call function 3. Function 3 finishes, returns to function 1. Function 1 finishes, returns to main. Main finishes, stack's empty. So let's let it restart and see if we got that right. So main, 1, 2, 4, 2, 1, 3, 1, main. I messed up there, but whatever. So that's the call stack. Yeah. Okay, heap. Very broadly speaking, the heap can be broken into static and object space. Static space, that's where we store classes, static methods, static variables, interfaces. And object space is where we store the objects we create. And that's going to have things for like, what's the object type, the values and fields stored in that object. That might include primitive or reference variables to other things in the heap. When an object is created, it's put into the object part of the heap. Then we have this garbage collection, which we've talked about a lot. And garbage collection is fantastic. But the problem is, you know, when something gets allocated in the heap, you know, if I come along and I say something like, some object equals new some object, I'm allocating memory in the heap. But I'm like, when I say new some object, I'm specifically saying, hey, go create a new object somewhere. But I never have to explicitly say, okay, go uncreate, go delete that object. And that's because Java and Python, but in a lot of other languages, have a built-in system called garbage collection, where garbage collection will go and look at your heap and say, okay, here's a thing in the heap that has no reference variable to it. And if there's no reference variable to this thing in the heap, I can never get to it. And if I can never get to it, it's as good as done. So we can free up that memory. In some languages, we don't need something from the heap that we've allocated. We need to, in some programming languages, when we don't need something from the heap that we've allocated, we need to deallocate it ourselves. We need to explicitly say, okay, delete this thing. So we've got new and delete keywords. In Java, we don't have the delete keyword because Java deletes things for us. But has anyone ever heard the phrase memory leak before? I think it was a bigger phrase from when I was younger, but less and less people know it these days. But if you're writing a program and you keep allocating memory and then you never delete it when you need it, when you don't need it anymore, you've created memory leaks. Like you have allocated memory that you don't need anymore. And so you have these things stored in memory that are just wasting space. So in Java and most other modern languages, if an object is not reachable anymore, then it can't be used. Thus, it is available for garbage collection. An object is not reachable when it can't get referenced, when we can't get reference to it anymore. So think of this link structure here. In the above example, there is a reference variable head in each of the node's next field. So imagine in my main, I have a reference variable called head. That's just a reference to some node. Now, I don't have reference to each individual node I've created in the heap. I don't have reference to each individual one. What I have is a reference to the head, which then has a reference to to a subsequent one, which has a reference to a subsequent one, and so on and so on and so on. So things in the heap can be referenced by other things in the heap, and it's still considered fine. But imagine I come along and say, okay, head, u equal null, for whatever reason. Well, suddenly, this right here isn't referenced by anything anymore. It references something, but that doesn't matter. I can't get to this if head doesn't point to it anymore. Meaning that Java's garbage collection can come along and go, okay, you, I don't need you anymore, so delete. Which then means this one doesn't have reference to anymore. So we could delete this, and then delete this. And so it creates this like chain of events of deleting things. Yeah, okay. For example, if we have head, yeah, okay, I just said that. If one of the links in the structure gets lost, all nodes after it get unreached. So if I lose reference to the head, the whole list is gone. If I lose reference to this one, everything after this is gone. So we need to be very careful about what we are referencing when. All the nodes after remove link are now deemed available for garbage collection. Okay. If head gets reassigned and will no reference to the first node in link structure, all nodes become unreachable. Example, head equals null. Okay. Even though all nodes, except for the first one, have references to them via their predecessor's next field, none are actually reachable anymore. In the end, all nodes end up being available. Yeah, okay, I just went over that. And then, who here has seen this phrase before? Yep. Okay, here's a little thought experiment for you. Based on if you have a sheet of paper in front of you, good, do this. Here is a method. And take what you just learned about the call stack and how whenever a method calls another method, it creates a new call frame, pushes it on the stack. And then we start executing that new method. Based on what we just learned about the call stack, what is this going to do? Here's a hint. Gonna do something, that's for sure. You're right, Devin. Crash. It will crash. In fact, let's prove this. Let's go lecture stuff. Where's my lecture one? There. In fact, IntelliJ is probably going to be like, okay, yes. IntelliJ is already warning me So in my main, I'm going to call uh-oh. And then uh-oh prints out we, and then calls uh-oh, which then will just print out we, and then call uh-oh, and then print out we, and call uh-oh, and then print out we, and call uh-oh. Let's see what happens if I hit run. Uh-oh. So we see the we's get printed out. There's a lot of them. I mean, look at my bar over here. But eventually Java says, okay, Stack Overflow error. We created a Stack Overflow issue. Every time we make a call frame, that takes up more space in our computer. So if we wrote a function that just keeps throwing more and more and more and more and more things on this stack, it's going to very quickly take up our RAM on our computer, which is no good. So, pardon me, a lot of these modern languages have built-in mechanisms that go like, okay, if you end up noticing like your stack is getting too big with these recursive calls, create a stack overflow error, because we've got a problem. And it's telling me exactly, like, here we go. Well, uh-oh called uh-oh, which called uh-oh, which called uh-oh, which called uh-oh, and so that is a stack overflow. So I'm going to actually get back to what Elongated said in one moment. System overload bloom. Haha, he said the thing. Thanks. So this would happen from pathfinders if they stuck and used on a huge maze. If it was recursive. Because, okay, Bob, you raise a good question. Because if you built a stack, then your stack is allocated on the heap part of your RAM, and your computer's fine with managing that really, really well. But when the call stack, which is in like the call stack part of your RAM, like the working memory part, that'll run out real quickly, real fast, and your computer wants to be very protective of that. So an interesting question, and your computer does something called paging too, where is if your RAM is getting too full, your computer will have a way of like putting stuff in RAM for longer term storage and then getting it back later. But elongated muskrat. So you raise an interesting point. Print forever. Well, yes, that's what would happen. But as a consequence of how these computing systems that we use work, it stops because it has this built-in trigger to be like, okay, stop. We've got a problem. But we have to be sure, like obviously we are programming on these computers, right? Like I get that. But remember that computation and computing and computer science is a separate thing from the actual computing machine we're using. Obviously, it's very much tied to these physical computers that we use, but one could build another computing system that was structured differently, and you could run something like that, and you've effectively made an infinite loop. So computing, the fact that this has a stack overflow is a consequence of how these physical machines work. But in terms of like what the unit, like in terms of the mathematical principles of recursion, there's no limit. So interesting. So, okay, stack overflow. So what we just did here was something interesting, because this right here is a function definition, right? We are defining a function called uh-oh. And the definition of the function uh-oh prints out we, and then is also defined by a function call to uh-oh, which is kind of weird, right? Because we have a function called, we are defining a function called uh-oh that is defined, part of its definition is itself, which doesn't really make sense, right? Like, what? I'm going to define uh-oh. Well, what's uh-oh? Well, it's uh-oh. that feels like I'm cheating. That feels like something's not quite right. Yeah. Okay, any questions about any of that? All right, in that case, on to recursion, one of my favorite topics. Okay. Before, I know in 161, I very briefly talk about recursion just a little bit. I want to start this discussion on recursion by pointing out something I think is a load of shit. Is students, when people start learning recursion, it's become like a joke, like, oh, recursion, it's so hard, oh, it's really tough. Yeah, no, it's not. And I think students hear other students talk about how hard it is. So then they get up all in their head about like, oh man, it's hard to wrap my head around this. Okay, it's not trivial, that's for sure, but it's not as hard as people seem to make it seem. So just go along with me on this. It's not as hard as people like to say. Former computer science students are terrible at getting new computer science students to learn anything because they keep telling them lies, like recursion is hard. No, it's not. So here's a list of people, right? How many people are in this line? And how do you count them? Someone tell me, how many people are here? It's not a trick question. At least 3.5, 15, 32, 15. Well, let's find out. Okay, so here's how I'm willing to bet that all of you who did count, all of you counted iteratively. But there's nothing saying you couldn't count this another way. So here's how I'm gonna say. I'd say the answer is, just by looking at the first person, the number of people in that line of people is exactly 1 plus the number of people after the first person. Would you agree? R2T2 said the right thing, I think. It's 1 plus however many are right here. Okay? Great. So all I need to do to answer this question is figure out just 1 plus x, where x is the remaining number of people. Great. But of course, you're not going to be satisfied with this answer, right? Because you're looking for a specific answer. And then I just show up and say like an asshole, like, oh, it's 1 plus the remainder. And you're going to, yeah, thanks, Dick. Like, that's not very helpful. Well, that's okay. Because all we have to do to say, okay, it's 1 plus the number of people in the remaining line. Well, how many people are in that line? Well, okay, well, it's 1 plus the remaining people in this line. Here, I'm going to copy this. No. Oh, I see what I did. Oh, no, I closed it again. For the simplicity of right now, we're going to leave it as this long. So, this is the 1 plus the remainder, right? So it's going to be 1 plus, yeah, I don't know. But the good news is, I have a really great way of counting how many people are in that remainder of the list. It's 1 plus the number of people in the remainder. So that's going to be, that's going to be our 1 plus, yeah, I don't know. But the good news is that's just 1 plus how many people are in the remainder of the list. Okay, well, that's easy. That's just the 1 plus the remainder. 1 plus. And well, the good news there is, well, to find out how many are in the remainder, that's just 1 plus how many in the remainder, which is a big question mark. And then finally, of course, let's go with black. How many people are in the remainder of the list? Well, it's 1 plus how many are in the remainder after, well, okay, oh, that's just 0. Oh, okay, so I know how many people are in this list. It's 1. So that's now a 1. So now, because I know the answer to this, I know how many people are in this part of the list. That's just 2. So all of this is replaced with 2. And based on that, now I know how many people are in this part of the list. That's the 2 plus the 1 person that comes in front. So all of that is 3. And now if I know that that's 3, I know how many people are in this list because that's the 1 plus how many people are in the remaining part of the list. So that's a total of 4. And then how many people are in the total list? Well, that's just the first person plus how many people are in the remainder of the list, which is 4. Isn't that a much better system of counting? Yeah, I think so. Of course, that feels a little ridiculous, but that is recursion. Okay, iterative definition versus recursive definition. An iterative definition of things are fairly natural to us. Recursion, on the other hand, may feel a little less natural, but it actually pops up a lot in our lives and in nature. Most processes in the universe that are happening aren't happening because there's a for loop. It's because there's some functionality that begets more of that same type of functionality. Recursion is very common in our universe. I mean, you can look at something like this. Okay, well, that's really pixelated. But how many people have ever woken up and saw a window that looked something crazy like this? Right on their window because ice started freezing and you're like, whoa, what a crazy pattern, right? It's got these like long branches and each of those branches have these branches coming off of it. And each of those branches have branches coming off of it. And each of those branches have branches coming off of it. Yeah, that is like a recursive process. It's just how these things are being formed, which is pretty cool. I hear boops, but why is this not updating? Well, whatever. Oh, people raise their hands. Wow. I know, R2T2. So, groups of people. Like the line of people example above, it may seem like a silly question because it's so intuitive, right? A group of people is defined as 2 people. This feels like a typo. Someone should go make a PR for this. Get rid of this or 2 people because it's 2 people or 2 people. Yeah, that's not right. This is an issue. Someone should go fix this. Go make a pull request. If you don't do it, I will, and you'll miss out the chance to get yourself on the website, which, by the way, we had a new contributor, console log. I don't know who you are, but congratulations on making that fix to the course content. Thank you very much. Well done. One step closer to that jumbo Snickers. But a group of people is 2 people, or 3 people, or 4 people, or and so on and so on and so on and so on and so on. But I mean, it would be kind of ridiculous to write out every possible definition of a group of people. Like, I could keep this list going, and that would work. But we can use this idea of recursion to define a group of people a different way. And chances are your brain is kind of doing it this way. You don't think of a group of people as this. You're probably thinking of it as something more along the lines of this, where a group of people is two people or something we would already call a group of people plus one more person. Chances are you already think of this like this, whether explicitly or not, you do. Because you don't think, is that a group of people? You don't go up some lookup table and be like, there's 7 people over there. Is that a group? Well, 1, 2, 3, 4, 5. No, you go like, well, okay, if 2's a group, 3's a group, 4's a group, 5's a group, and so on and so on and so on. This is a much cleaner and more succinct definition of a group of people. This, I can describe it in 2 lines. Where here, I would need an infinite number of lines. -1, because we don't need this line. So we can use a recursive definition, and the reason this recursive definition is so elegant is because it defines itself in terms of itself. A group of people is 2 people or a group of people plus 1. So the definition of a group of people includes the use of the definition of a group of people. Which again, this might feel weird and awkward and uncomfortable, but your brains are already experts at this. Remember all that talk of the call stack? How I was saying like, oh, you ever need to debug something and you need to, before you can fix that, you have to fix that, and before you can fix that, you need to fix that. You haven't gone and created a call stack. You're thinking about these things recursively, whether you like it or not, right? You go down one more level and then you fix that. Then you can come back up a level to fix what you were working on. And then you can go back to fix what you were working on before. You're already all experts at recursion. It's kind of funny because it feels as if the iterative definition is more natural to you, when that's really not the case. It's because all of our mathematics upbringing is very iterative, but recursion is just as valid. And interestingly enough, anything you do with iteration, you can do with recursion, and vice versa. Though just because you can doesn't mean you should. But it's true. Okay. Based on this definition, if I ask you if 2 people are a group of people, the answer is clearly yes, the first point. By definition, a group of people is, 2 people is a group of people, yes. But if I ask you if 4 people is a group of people, you might need to do some digging, right? If we want to be very explicit about it, we'd have to do some digging. We'd say, okay, well, in order to tell you if 4 people is a group of people, I need to know if 3 people is a group of people. If 3 is, then I know 4 is, since 4 is then be, another typo, someone can fix this. Then I know 4 is, since 4 is then be a group of people plus 1 more. Another typo, someone can fix this. To know if 3 people is a group of people, I must know if 2 people are a group of people. And I know by definition that 2 is, in fact, a group of people. Therefore, 3 is a group of people because it's a group of people plus 1 more. Therefore, 4 is a group of people because it's 3, which is a group of people because we just figured that out. And 3 plus 1 is 4, so 4 is obviously a group of people. This is me going crazy deep in the thinking here, which we're going to want to do when we program. But realistically, your brain, if I ask you something like, oh, is that 4 people a group of people? You are doing this like that. You don't have to go like, well, okay, there's 7 people over there. So 7 is 6. Is 6 a group? No, okay, 6, I don't know. I can't. Is that 5? Is 5 a group? Obviously, you're not doing that. I mean, in coding, we'll need to be a little bit more explicit, but this is just it. This is the idea. And someone, go make a PR to fix this. If 3 is, then I know 4 is, since 4 is then be a group of people plus, someone can fix the grammar on that. So in the above recursion example, you would notice a base case and a recursive case. This is the base case. This is the recursive case. The base case involves something with a clear definition, and the recursive case is one that defines itself in terms of itself. Warning, although there is no hard rule saying that you need a base case, And there are examples of situations where you would not include one. Not including a base case is a recipe for disaster. Remember the uh-oh from topic 18. For our purposes in this course, we're always going to have a base case. Don't get fancy. And we're out of time. Group of people. Yep. All right, hopefully you all go, is my brain supposed to hurt? No, because you're thinking too hard. Is recursion faster or something? No, recursion's actually way slower. But we'll talk about that later. All right, we'll wrap up here. Obviously, we're out of time. And I'll see you all tomorrow.